In this video, we are going to look at derivatives of inverse trigonometric functions. But before we do, we need to look at some rules. Rule 1. The derivative of inverse sine of x with respect to x is 1 over the square root of 1 minus x squared. Rule 2. The derivative of inverse cosine of x with respect to x is negative 1 over the square root of 1 minus x squared. Rule 3. The derivative of inverse tangent of x with respect to x is 1 over 1 plus x squared. Rule 4. The derivative of inverse cotangent of x with respect to x is negative 1 over 1 plus x squared. Rule 5. The derivative of inverse secant of x with respect to x is 1 over x times the square root of x squared minus 1. And Rule 6. The derivative of inverse cosecant of x with respect to x is equal to negative 1 over x times the square root of x squared minus 1. Now, the directions say to find the derivative of the function, simplify where possible. So let's take a look at example 1. Suppose y equals the inverse tangent of x raised to the second power. So what I'm going to do is I'm going to let u equal the inverse tangent of x. That's the inside function. As a function of u, we can say y equals u squared. Now, du dx is equal to 1 over 1 plus x squared. It's one of the derivative rules for inverse trigonometric functions. dy du is equal to 2u. Okay? Now, dy dx is equal to dy du times du dx. Okay? But dy du is 2u. And then du dx is 1 over 1 plus x squared. But if we notice, u is equal to inverse tangent of x. Therefore, dy dx is equal to 2 times the inverse tangent of x divided by 1 plus x squared. And this is how we do example 1. So this is a chain rule problem. Now, let's take a look at example 2. It's subtly different, okay? Suppose y equals the inverse tangent of x squared. So what's the inside function? The inside function is this x squared. So I'm going to let u equal x squared. As a function of u, we can say y equals the inverse tangent of u. What is du dx? Well, that's just 2x. And then dy du is 1 over 1 plus u squared. Okay? Now, we get to put it together. So dy dx is equal to dy du times du dx. Now, if we go back, dy du is 1 over 1 plus u squared. And then du dx, we go back, that's 2x. So we can go forward and put 2x. But remember, u is equal to x squared. So if we substitute that in, we can say dy dx is 2x divided by 1 plus x raised to the 4th power. And that's example 2. So let's go ahead and we're going to take a look at example 3. Suppose I had the following. Suppose I had y equals arc sine of 2x plus 1. So I'm going to let u equal 2x plus 1. That's the inside function. As a function of u, we could say y equals arc sine of u. Now, du dx is equal to 2, right? dy du is 1 over the square root of 1 minus u squared. Now I get to substitute everything in. So dy dx is dy du times du dx. So we get 1 over the square root of 1 minus u squared. And I'm going to take that and I'm going to multiply by 2. Because that's what du dx is. So, but remember, u is 2x plus 1, okay? So I'm going to substitute that in. So we can say dy dx is 2 divided by, and then we get the square root of 1 minus, and then if we go back, remember u is 2x plus 1. So I'm going to replace u with 2x plus 1. So it's 1 minus the quantity 2x plus 1 to the second. And this is equal to 2 over the square root of 1 minus, in parentheses, 4x squared plus 4x plus 1. Okay? And if I distribute the negative in, I get 2 over the square root of 1 minus 4x squared minus 4x minus 1. But the 1's cancel. And at the same time, I'm going to factor out a 4. And when I do, I get negative x squared minus x in parentheses. Is that okay? Because what's the square root of 4? The square root of 4 is 2. And so I'm going to cross this 4 out with that 2 on top. And in simplified form, we can say dy dx is 1 over the square root of negative x squared minus x. And I'm done. So I will not go further than that. And this right here was example 3. So we're going to go ahead and take a look at example 4. Suppose I had the following. G of x is equal to the inverse cosine of square root of x. So I'm going to let u equal the square root of x. And then as a function of u, if you don't mind, I'm going to write y is the inverse cosine of u. And this is where y equals g of x. Okay? And so du dx is 1 over 2 times the square root of x. dy du is negative 1 over the square root of 1 minus u squared. Like so. And then it just becomes applying, right? So we can say dy dx is dy du times du dx, okay? Now, dy du is negative 1 over the square root of 1 minus u squared. Du dx is 1 over 2 times the square root of x. And in context, x is greater than or equal to 0. In fact, x is strictly greater than 0 because if x is 0, you're dividing by 0, and that causes a problem. Now, don't forget, u equals the square root of x. So, therefore, dy dx is equal to, I'm going to write 1 over 2 root x, and I'm going to take that times negative 1 over the square root of 1 minus the square root of x squared. Okay? So dy dx is negative 1 over 2 times the square root of, and then x times 1 is x minus x squared. So I'm just combining. So I'm taking square root of x times the square root of 1 minus x. And this is what I come up with. Okay, and that was example 4. And if anything, what you can do is take note that this says g prime of x is equal to negative 1 over 2 times the square root of x minus x squared. So it may be more complete to write g prime of x instead of dy dx, like so. Now, let's take a look at example 5. Suppose I had the following. So f of x is x times the inverse secant of x to the third power. Okay. Now, I'm going to start here. I'm going to let y equal the inverse secant of x cubed. We need to get a handle on that first. So my inside function, I'll use set, just to change up the wording. Set u equal to x cubed. So y is the inverse secant of u. Okay. Now, du dx is 3x squared. dy du is 1 over u times the square root of u squared minus 1. Okay. And dy dx is dy du times du dx. Okay. And let's remind ourselves, dy du is 1 over u times the square root of u squared minus 1. Du dx is equal to 3x squared. Okay. But remember, u is equal to x cubed. So therefore, dy dx is 3x squared over, now I'm going to get x cubed times the square root of x raised to the 6th power minus 1, which is 3 over x times the square root of x to the 6th minus 1. So takes a bit of work to get the inverse, the derivative of the inverse secant of x cubed. But once we have it, we can now go back and apply the product rule. Now, let's come back here. Suppose f of x is x times the inverse secant of x cubed. So, and I want f prime of x. So I'm going to take the derivative of the first function, which is 1, and I'm going to multiply it by the second function, which is inverse secant of x cubed. I'm going to go plus, because we're dealing with a product, right? So when you do the derivative of a product rule, we have to have a plus. And then I'm going to write x times. Now, let's go back and remind ourselves. The derivative of inverse secant of x cubed with respect to x is this mess, right? So I'm going to write 3 over x times the square root of x to the 6th minus 1. So it's interesting. Now notice how the x's cancel, and we get inverse secant of x cubed plus 3 over the square root of x to the 6th minus 1. Now, this is where you want to talk to your instructor. Your instructor might, A, want you to rationalize, or B, want you to put, get a common denominator. So, in other words, I'm going to leave it this way. F prime of x, you're going to get the square root of x to the 6th minus 1. I'm going to take that, and I'm going to multiply by inverse secant of x cubed. I'm going to add 3, and I'm going to divide by the square root of x to the 6th minus 1. And that is going to conclude this video where we did derivatives of inverse trigonometric functions. So, and you notice again, from the second to last line to the last line, I just got a common denominator. So, okay, 5 examples of derivatives of inverse trigonometric functions. Thank you.